In this survey of optics, we have discussed the nature of light, the speed of light, the electromagnetic spectrum including visible light, the reflection of light with mirrors, and the refraction of light with lenses. Light is made up of photons. Photons are tiny bundles of energy that behave as both waves and particles. The speed of light in a vacuum is 3 times 10 to the 8 meters per second. This can be calculated, as can all waves, by multiplying wavelength times frequency. Wavelength is measured in meters as the standard unit. Frequency is measured in hertz, which is a wave per second. Therefore, the unit for the speed of light is meters per second. There is an inverse relationship between wavelength and frequency. As you consider the entire electromagnetic spectrum, from radio waves with the longest wavelength to gamma rays with the shortest wavelength, the longer the wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency. All forms of electromagnetic radiation travel at the same speed. As you study, make sure that you know the order of the various types of electromagnetic radiation. If we examine that relationship in terms of the visible light colors, which include red, orange, yellow, green, blue, indigo, and violet, as wavelength increases or is longer, the frequency decreases. Fewer waves come by per second. The inverse is true. With the shorter wavelengths, we have more frequency. With increased frequency, we also have increased energy. Therefore, we can imply that ultraviolet light has more energy than red light. While all colors of light travel at the same speed, 3 times 10 to the 8 meters per second, as they're refracted, they bend at separate angles, which is why prisms make the little rainbows. We can use Planck's constant in this equation, E equals h nu, to calculate the energy that a photon of light can have. There is a direct relationship between frequency and energy. As frequency increases, energy increases. Here's a sheet that compares the lenses to the mirrors. We have concave and convex, but mirrors and lenses have the opposite effect. Concave mirrors converge light, whereas convex lenses converge light. And then the opposite is true, as will follow suit. Convex mirrors diverge light, whereas concave lenses diverge light. Study these diagrams to increase your likelihood of keeping these straight. When you take the test, you might consider jotting these down for yourself in the corner. Read through this sheet to confirm what you know to be true about mirrors and lenses. For converging lenses or mirrors, light rays that are parallel to the principal axis will converge at the focal point. For lenses, an image formed through the lens on the other side constitutes a real image, whereas an image formed on the same side of the lens as the object itself is considered a virtual image. For the convex lenses, most of the images formed wind up being real, inverted, and in most cases minified. That depends on the position of the object of the lens. However, if you put the object in front of the focal point, then everything flip-flops and you get a virtual and upright image. Now with concave lenses, the images are almost always virtual, upright, and possibly minified, depending on the position of the object. Refraction is the bending of light as it passes through a medium. This is a function of the speed of the light changing as it goes through the material. The index of refraction is the ratio of the speed of light to the velocity of light in the medium. There are some relationships about this index of refraction, which is represented with letter N. The greater N value means the more change in speed and the more bend to the light rays. One type of mirror is a plane mirror. With plane mirrors, the law of reflection applies, which says that the angle of incidence is equal to the angle of reflection. Therefore, an image formed in a plane mirror will always be upright. It will also be placed equidistant from the object to the mirror. For example, if someone were to stand 3 feet in front of a mirror, their image would appear to be 3 feet into the mirror. There are also curved mirrors, such as concave and convex. In these examples, the attributes of the image formed are dependent on the placement of the object in relation to the focal point and the center of curvature. Take time to study these so that you are prepared to answer general questions about them. Convex mirrors, like those found in the security mirrors in the corners of stores or rear view mirrors, always create a virtual, upright, and reduced image. This is the format of the equations that are printed on the test. Notice that on the right-hand side in red are the equations dealing with the electromagnetic spectrum and light itself. The constants, such as Planck's constant and the speed of light, are given. On the left we have the mirror equation and some of its derivations to the right of that, and also the magnification equation. These equations work for lenses identically to the way that they work for mirrors. And then at the very bottom on the left, we have the equations that deal with refraction, N being the index of refraction. Theta sub c refers to the critical angle. Make sure that you're familiar with where these equations are and how they are used.